On page 505, we're going to talk about a similarity transformation. We have two learning targets. We're going to identify a dilation, which is a similarity transformation, the scale factor of a dilation, and the center of dilation. And the second learning target, verify similarity after a dilation. I'm going to give you more of a roadmap of how you do that instead of testing you on you doing that. Okay? So that one we're going to do, we're going to be a little incomplete on that learning target. But that's okay. Because we're also going to do dilations when we get to Unit 9. So that's why I don't want to spend just a tremendous amount of time on them right now. But we need to know what one is. All right? So we've talked about transformations before. And the transformations we've talked about before were congruence transformations. When we did a translation, when we just slid a figure along the paper, it did not change size. The resulting image was congruent to the pre-image. Or if we did a reflection, when we flipped a figure over, the resulting image was congruent to the pre-image. Or if we did a rotation, where we turned a figure, the resulting image was congruent to the pre-image. So those are congruence transformations. They're called rigid motions. Okay? The dilation is when we shrink or enlarge. So we will reduce or enlarge a figure. The resulting image will be similar to the pre-image, not congruent to the pre-image. So on page 505, we have some definitions you need to know. A dilation is a transformation that enlarges or reduces the original figure proportionally. That's how you get the similar figures. The sides are proportional. Since a dilation produces a similar figure, a dilation is a type of similarity transformation. Dilations are performed with respect to a fixed point called the center of dilation. So, in the figure you see here on the screen, point O, the origin, O for origin, is the center of dilation for this similarity transformation. Okay? If we start with triangle ABC, and right now I'm not going to have you do your own dilations. I'm just going to have you recognize them. Okay? So look up here at the screen. If triangle ABC is our original figure, our pre-image, and then we dilate it, that can mean that we enlarge it, or it can mean that we reduce it. If it gets bigger, we enlarged it. If it gets smaller, we reduced it. So that's not complicated. But here's what this center of dilation thing is all about. Let's say that the green figure, triangle JKL, is twice as big. So let's say that the scale factor from the blue figure to the green figure would be 1 to 2. Or of the green figure to the blue figure would be 2 to 1. That's the way we would have talked about this before now, right? Okay, either way. So the scale factor of the green to the blue, the new figure to the old figure, would be 2 to 1, meaning that every side of the green triangle is 2 times bigger than the side from the blue triangle it corresponds to. If, when we make these, and I'll show you how to make these later, but here's how you make it. The distance from the center of dilation to A, keep going in that exact same direction, go twice as far, and put point J right there. That's how you get a scale factor of 2, because you went 2 times further. Okay? So whatever the distance from the center to B is, go twice that distance and put K. Whatever the distance from the center to C is, go twice that distance and put L, and that guarantees a scale factor of 2. If we had gone 3 times the distance, the scale factor would be 3. If we went, now, and this is where it can get weird. If we went like 5/4 that distance, well, then the scale factor would be 5 to 4. And it can get complicated, right, once you start doing fractions. Okay? So the scale factor of a dilation describes the extent of the dilation. The scale factor is the ratio of the length on the image to its corresponding length on the pre-image. We're used to the idea of scale factor. What you have to know for a dilation is this, that when you make the scale factor, you always put the new figure lengths as your numerator and the old figure lengths as your denominator. It always works that way. You always put the lengths of the new figure on top, and then the length from the old figure that corresponds to it goes on the bottom. It's got to be that way. And to use the words the book uses, the new figure is called the image. The original figure is called the pre-image. Image and pre-image. New and old. And then to repeat myself, if the new figure is larger than the original figure, it's an enlargement. If the new figure is smaller than the original figure, it's a reduction. Those are your only two choices. So, let me make up some numbers. So instead of having a scale factor of 2, like I said before, what if the length of JK was 3 and the length of AB was 2? Now the scale factor would equal new figure or old figure, 3 to 2. What if JK is 7 and AB is 4? What would the scale factor be now? 7 to 4. Make sense? Okay. Now, something you need to know that's not in this section, that whenever you have similar figures, the ratio of any pair of corresponding parts also equals the scale factor. So if we have two triangles that we know are similar, and we're making a ratio out of their altitudes, the ratio of the altitudes also equals the scale factor. Or if we drew in medians, remember what a median is? Goes from a vertex to a midpoint of the opposite side. If we drew in corresponding medians, the ratio of those also equals the scale factor. So the ratio of any pair of corresponding parts also equals the scale factor. That comes in handy every now and then. Okay? All right. Now, the enlargement and the reduction. The easiest way to tell which you have is by looking at the figures. If the new figure is bigger than the old, it's enlargement. New figure smaller, it's reduction. But look, you can also tell from the scale factor. If the scale factor is greater than 1, it's an enlargement. If the scale factor is less than 1, it's a reduction. Now, technically speaking, there can be negative scale factors. I'm not ready to deal with those. What that does is it flips the new figure to the opposite side of the center of dilation. So for the time being, we'll pretend the scale factor is always positive. If it's greater than 1, we have an enlargement. If the scale factor is less than 1, we have a reduction. Let's do some from assignment. So flip on over to page 508. In a minute. Flip on over to page 508. And the directions for number 1 say, to determine whether the dilation from A to B is an enlargement or a reduction. Now, this can be a little confusing. When they say it's from A, that means A is the original figure. Okay? So the blue triangle is the original one. The green one is the new one. So, is the green triangle larger or smaller than the blue one? It's larger, so our first answer is that this is an enlargement. Then we have to find the scale factor. The scale factor always goes new over old. Now, make this, and I'll use K for scale factor, make this as simple as you can. All I need to get the scale factor is one pair of corresponding sides, or the lengths of one pair of corresponding sides. So, would you rather use the distance formula to figure out that length and that length, or this one and this one, or would you rather count spaces to find the length of that side and the length of the side that corresponds to it? I'd prefer to count spaces. So, scale factor equals, remember, it's new over old. So first, let's count the spaces and find the length of that new side, the green one. 1, 2, 3, 4, 5, 6, 7, 8. 8 over, and then count the spaces for the blue side, and you get 4. Now, we prefer to have our scale factor reduced. Well, doesn't 8 to 4 reduce to 2 to 1 or even 2? So I would prefer to see on the quiz 2 to 1 or 2. Okay? I don't care which, 2 to 1 or 2, but I want to see it reduced. Think you're catching on? All right. Doing those problems is a little simpler than you might have guessed. Number 2. It's from A. So A is the original one, and B is the new one. Well, is B larger or smaller? Smaller. So this time we have a reduction. No. Always do the new one on top. If we stick with A and B, it's always B on top. Okay? All right, so the scale factor. Now, I can count spaces either vertically or horizontally. If I go horizontally, I got to estimate as halves. If I go vertically, I don't have to estimate anything, do I? The length of that side right there is what? 2. And then the length of this side right here that corresponds to it is what? 4. And when I reduce that scale factor, I get 1 to 2, don't I? If you did it the other way, you got 3 over 6, then you would reduce that and also get 1 to 2. Okay? So either way, we ought to come up with the same scale factor once we simplify it, shouldn't we? All right? So far, so good? All right, number 3. The dimensions of a regulation tennis court are 27 feet by 78 feet. The dimensions of a table tennis table are 152.5 centimeters by 274 centimeters. Is a table tennis table a dilation of a tennis court? Now, I'd never thought about it until I worked this problem, but I would have thought, well, yeah, probably. Let's see. We really just need to see if the figures are similar, right? If the figures are similar, then the table tennis table really is a dilation of a tennis court. It would be a reduction, but it's a dilation if the figures are similar. Well, let's see if they are. We know how to tell if figures are similar. If they're similar, the corresponding sides have to be proportional, right? Let's see if the corresponding sides are proportional. So, the short side of a tennis court is 27 feet. The short side of the table tennis table is 152.5. The long side of a tennis court is 78 feet. And the long side of the table tennis table is 274 centimeters. So the question now is, are those ratios equal? Well, let's get a calculator out and decide. So let me open up the calculator. Okay, so if I take the one on the left, if I take 27 divided by 152.5, math, fraction, enter, I get that as a fraction. Let's see if 78 divided by 274, math, fraction, enter. Oh, they're not equal. Since the ratios are not equal, the corresponding sides are not proportional. If the corresponding sides are not proportional, are those figures similar? No. And if the figures are not similar, then that is not a dilation, because a dilation results in similar figures. So, after all of this, what do we write as our answer? We say no, then we're supposed to explain. Because corresponding sides are not proportional. Now, I don't want to get sidetracked, but I just have to make this observation. If you call that a table tennis table, but instead you were playing ping pong, would you call it a ping pong ping? Number 4. Verify that the dilation is a similarity transformation. And then, now let me tell you how we would instead of us actually doing it. Okay? When it says verify, they're not asking you if it's a dilation. They're telling you that it is. Right? So how would we verify? Well, we've got different methods. These are triangles. So we could use angle-angle similarity, side-angle-side similarity, or side-side-side similarity, right, for a triangle. Now, when it's on a coordinate plane, we can't always tell if angles are congruent, but we can figure it out, right? So listen. I need you listening instead of writing. Here's what you might do. You might look and say, okay, angle A is in both those triangles. It's congruent to itself. Then, if I found the slope of DE and the slope of BC, and they turn out to be parallel, if they are parallel, wouldn't these two angles be congruent? Because corresponding two parallel lines cut by a transversal, corresponding angles are congruent. So that's how we would try to use angle-angle similarity, by finding the slope to see if another pair of sides are parallel, and then using stuff, I think that was chapter 3, way back when. If two parallel lines are cut by a transversal, corresponding angles are congruent. Side-angle side is probably the least satisfying. I would go for side-side-side similarity next, which would involve using the distance formula to find the length of all three sides of the blue triangle, the length of all three sides of the triangle. Then we would have to make ratios out of those and see if the ratios are equal. It'd take a while, wouldn't it? We could do it. You know how to do it. It would take a while. So that's the way you would verify. All right? On one like number 5, it's also a triangle, so I'd be doing the same thing. I might find the slope of LK and the slope of SR, and if they are parallel, then I would know that that angle is congruent to that one. I would also know that that one's congruent to that one, and I can tell right off the bat angle J is congruent to itself, so that'd be one way. Another way, use the distance formula, find the length of all the sides, make your ratios, make sure they're equal to each other. So verifying takes work. That's just all there is to it. Okay? All right. Now, I want you to flip all the way over to page 660. So in your book, all the way over to page 660. In a couple of weeks, when we do Unit 9, we'll be on page 660 again. But I want to go ahead and give you a little bit of a sneak preview of what we'll be doing with dilations at that time. Okay? Let me tell you how dilations work on a coordinate plane whenever the center of dilation is the origin. Okay? If you have a figure on a coordinate plane and the center of dilation is the origin. On a coordinate plane, the origin is where the x-axis intersects the y-axis. It's the point 0, 0. To find the coordinates of the dilated image, to find the coordinates of the new figure, all you have to do is multiply all the coordinates of the original figure by the scale factor. So if we call the scale factor k, if a point on the original figure has coordinates x, y, the corresponding point on the new figure will have coordinates scale factor times x, scale factor times y. So it's actually easy to do on a coordinate plane. Here's what I'm talking about. This is number 5 on page 663. So watch what I'm doing here. Yeah, write these down. Sketch you a coordinate plane real quick. Doesn't have to be a good one. Just sketch a coordinate plane. It doesn't matter. And then let's graph the points they give us. So W is at 0, 0. Look, all you got to do is this. Y'all don't just do this. Just do. All right, so we've got W. X is 6, 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then Y is 6, 0. There's W, X, and Y. And let's connect them. 6, 6, and 6, 0. Do what? Okay. Now, according to what I just told you, to get the coordinates of the new figure, you just multiply the coordinates of the original figure by the scale factor. So, and look, I'm even going to make the new points really easy. The point that corresponds to W, I'm going to call W, and I put a little mark there. It looks kind of like a apostrophe. That's called a prime. I'm just going to call it W prime. The scale factor is 1.5. So 0 times 1.5 is still 0. The other 0 times 1.5 is still 0. So W prime is the exact same point as W. Now I'm going to find X prime. To get the X coordinate of X prime, I multiply 6 by 1.5. What is 6 times 1.5? 9. Well then, what's the other 6 times 1.5? So X prime is 9, 9. So X prime goes out there. Then Y is 9, 0. So that's y prime. And there we are. So isn't it fairly easy to make a dilation as long as the origin is the center of dilation? It really is. Yeah, I know. That's why I got rid of mine, so that I didn't have an unfair advantage over you. Yeah. You can't daydream. Yep. You take the coordinates of the original figure and multiply them both by the scale factor. All I did is I multiplied the coordinates of w by 1.5 and got w prime, then the coordinates of x by 1.5 and got x prime, those by 1.5 got that, then I just graphed them. Yep. All right, let's do another one, because this can be easy. Yeah. All right, so here we go. Number 6, still on page 663. You are trying to make your figures look too good, some of you. So there's my xy plane. Q is negative 4, 4. So 1, 2, 3, 4 to the left. 1, 2, 3, 4 up. That's where Q goes. R is negative 4, negative 4. So 4 from the origin, 4 to the left. 1, 2, 3, 4 down this time. That's R. S, X coordinate of 4, Y coordinate of negative 4, and T, X coordinate of 4, Y coordinate of 4.
So it's all 4, 4, 4?
So that's kind of nice. Now, oh, forgot to connect them to make our figure. So that's the graph of RST. Now let's get the coordinates of the dilation when the scale factor is 1/2. Let's get the coordinates of Q prime. We multiply the coordinates of the original point by the scale factor. So what's negative 4 times 1/2? Negative 2. What's 4 times 1/2? Positive 2. So look where Q prime goes. What are the coordinates of R prime?
2, 2.
Not 2, 2. Negative 2, negative 2.
And 2, negative 2.
And then 2, negative 2. And then 2, 2. And there you go. You think you got it? I think you got it. And here's your assignment. Page 508, 1 through 20, and 28 through 31. Page 508, 1 through 20, 28 through 31.